What's up, Access people? I'm both grateful and sad to say that this is the last chemical engineering video that you're going to get to see this semester. Since it's our last hurrah, I want to give you the lesson that I wish I received when I was a freshman in chemical engineering. Specifically, what is chemical engineering? We talked about process engineering earlier and we talked about reactions after that, but if someone had to provide me a full list of what skills a chemical engineer was supposed to have and what they could do with them, I think that would have saved me and a lot of my fellow chemical engineering students a lot of hassle in terms of finding a field to study. So let's talk about what skills a chemical engineer is supposed to have. Let's think about a typical task for a chemical engineer. Let's say that our company just came out with a vaccine for COVID-19 and we need to make this vaccine for the world to use. So we need to make it quickly, efficiently, cheaply, and effectively. So first off, we're going to need a reactor, right? And this thing will use all the physics and chemistry that we know to produce the molecules that will go into the vaccine. We're chemical engineers, so by definition, we're going to need to deal with chemical reactions. But in order to use the reactor, we're going to have to put stuff into it and take stuff out. Are we going to do this one at a time? No, we're gonna do this with pipes that carry fluid in and out of the tank continuously. So chemical engineers need to understand how fluids move, how they interact, and how we can move material from one place to another without any problems. And after we can move things around and react them, we might need to separate a bunch of products, right? So what's an easy way to do this? We could turn one into a gas and one into a liquid. Therefore, we're going to need to know the thermodynamics that justifies how we separate materials and make them change phase. So will our materials naturally separate like oil and water, or will we have to boil one off? That's a chemical engineer's job. And then sometimes we've isolated a bunch of products that need to be brought together. So therefore, instead of separating, we need to know how to mix things as effectively as possible. Is it possible to mix oil and water? If you put enough energy into the system, then it should be. And this is the sort of thing that a chemical engineer needs to know. And again, we're going to need to move all these fluids around our plant using pipes and fluid mechanics. So what classes does a chemical engineer need to take? Well, we need to understand reactor design, reaction kinetics, and thermodynamics for our reactions. And to mix things, we'll need to know about a subject called heat and mass transport. For separations, there's a whole class dedicated to this topic, and thermodynamics is the precursor for that field of study. And to move fluids around, that's all fluid mechanics. Last but not least, we need to consider our overall process, right? How much material do we actually need to make these vaccines? How much will our process cost? How much energy will we produce versus how much energy is required? And how will we automate this process to work without human intervention? And can we model our process mathematically to know specifically how much we put in, how much time it'll take, and then how much we produce? All of these questions can be answered by chemical engineers with a knowledge of material and energy balances along with controls. So now that you sort of know the kind of subject matter that a chemical engineer needs to be able to take care of, let's delve into a few of these subjects in more detail. Personally, I think that fluid mechanics is pretty sick. I'm actually taking this course right now, and although there's a lot of math involved, the impact of the math you're doing sometimes yields really dope consequences, right? One of these things is called Stokes flow. This is the kind of flow that occurs when you have what's called a low Reynolds number, right? And all that you have to know about this is that if your flow is pretty thick, so something along the lines of honey or jelly rather than water or milk, then you'll experience low Reynolds number, right? When you apply a stress to a liquid, you cause it to flow. But when you apply a stress to a liquid with a low Reynolds number, you get a really interesting property. What happens is you can induce the flow in one direction just by applying a force, and then if you apply the opposite force, you can make the flow move backwards in time. This video shows exactly that process. The flow causes the dye to diffuse as the stress is applied to the fluid, but if you apply an exact opposite stress for the same amount of time, you return to the exact same position. So you can verify this mathematically by solving a few differential equations, but I think this video is a lot cooler. And believe it or not, a lot of the ideas shown here are important for things like pipe flow, which is absolutely essential to understand if you're going to make something like a COVID-19 vaccine. You know how I said that liquids have this thing called a low Reynolds number? This number is closely related to something called viscosity. You might have heard certain fluids being like more viscous than others. For example, water isn't viscous, but honey is. Some fluids have really interesting properties associated with their viscosities. These fluids are called non-Newtonian fluids. You can see one here. As you apply a really high stress, the fluid acts more like a solid. This allows people to run across a pool of the fluid no problem. That's because they're basically running over something acting like a solid when they're in contact with it, but like a fluid otherwise. Pretty cool, right? If you were an engineer making ketchup, toothpaste, or shampoo, these sort of properties become really important. Another subject that I think is super cool is thermodynamics. At its core, it's about how energy moves around in the system, especially a really small scale system. Thermodynamics is one of the reasons why when you scramble an egg, you can't make it go back to a yolk and an egg white, right? There's only one arrangement with the yolk and the egg white separated, but of billions of arrangements where the yolk and egg white atoms are mixed. Therefore, due to probability, the egg stays scrambled rather than sunny side up. And thermodynamics can do a lot of things, like tell you how much heat is produced in a reaction. If you want to know how much heat is produced when you use your fireplace, you would have to use thermodynamics. And if you want to know how much energy your refrigerator uses to cool something down, that's also thermodynamics. In chemical engineering, there's one area of research that I find super interesting, and that's something called molecular simulation. This whole field relies on thermodynamics. It uses the properties of thermodynamics to simulate how small-scale systems move to such a degree of specificity that we can simulate entire proteins interacting on the molecular level. In this video, you're watching a simulation of a protein going from an unfolded to a folded protein state. Needless to say, if you can predict how an unfolded protein folds, then you might be able to cure cancer. I'm not even kidding. Right? Learning how to predict this sort of thing requires us to understand the process, and in order to understand the process, we need to use simulations. In this video, we're watching ice melt. These water molecules start out ordered in a solid structure, but with enough energy, they're forced to break apart their hydrogen bonding network and form a liquid. The specifics of this process are also not well understood, and simulations are the gateway into finding this out. So, as you can see, thermodynamics is important both from an engineering and a scientific standpoint. This was a short introduction into the types of skills that chemical engineers need to have. Chemical engineers have been using these foundational skills to conquer a range of problems. Fritz Haber used these principles to develop a process for ammonia production that significantly increased the production of fertilizer, which laid the foundation for modern societies. Millions of people would have starved without his work. A guy named Bob Langer, who's the most published engineer in history and currently a professor at MIT, used principles in chemical engineering to revolutionize drug delivery, which made so many new types of medicine possible. Again, millions would have died without his impact. And most recently, chemical engineer Frances Arnold recently won the Nobel Prize in Chemistry for her work on the engineering of enzymes for chemical reactions. Again, super important work. So studying a subject like this makes a real difference in the scientific and engineering communities, not to mention the world at large. I hope that these past few videos have motivated you to study the subject, or at the very least, have given you a respect for the field as a whole. So that's everything for chemical engineering during this one semester of Access, and I wish you the best. Bye.